Okay, YouTube, in this video we're going to explore some basic properties of logarithms just now that we kind of have an idea of how to rewrite them into exponential form if we care to do so, or writing exponential things into logarithmic form if we need to do so. In this video we're going to do the former rather than the latter. So we're going to say we'll need to be proficient in evaluating logs. Of course, this can be accomplished by rewriting expressions in logarithmic form into exponential form. And I get this question a lot: how do you know when you need to rewrite it into exponential form? Well, first of all, if you can't just tell me that the exponent here that I would take 10 to the power of to turn it into 100 is 2, then what we're going to need to do is rewrite it into a form that we're probably a little bit more familiar with. And so let's just try this. If we did write an exponential form, what would that tell us here? So first things first, we're trying to figure out, log base 10 of 100 here. And I'm going to write, like is equal to a question mark. You're going to see that maybe many textbooks write like equal to y, of course. If I wanted to find this here, remember that we could write this into exponential form by doing this little loop-to-loop here. And so what we're really saying is 10 to the power of y equals 100. And so really what we are asking here is, what could I take 10 to the power of to get 100, of course. But I can get an idea on this a little bit more easily if I just rewrite this in exponential form. So let's see how much that helps us. Like with all of these logarithms that we see here, that we always get asked to evaluate without a calculator because, of course, we're dealing with nice little, exponents that are either perfect fractions or nice integers. So let's look at this here. We say log base 5 of 125. That's how we'd read this here. Log base 5 of 125. What would we get if we rewrote this into exponential form? And so let's go around the loop here. We say our base, of course, is 5. 5 to the power of y turns into 1 over 125. Now, one thing I would mention is this. You need to recognize that 125 is 5 to the third power, but also this, if I said, what could I take 5 to the power to get, 1 over 125, you notice that this is the reciprocal kind of relationship here that you would see if you had a negative exponent here. So for instance, if this were like a negative 3 here, of course we would get not 125, but 1/125th. And so we'd say y here is negative 3. Excuse me. So looking at this next one here, this is an interesting situation. If we were to say, of course, equals a question mark or equals y, go around, rewrite this exponential form, we say 36 is our base. We say 36 to the power of y equals 6. Now, you might say, well, did I take this to a negative exponent? Well, I can't think of anything. Well, I guess I can. I can think of something off the top of my head, but, many people can think of a thing off the top of their head. You take 36 to the power of to get 6. So I guess I would say that 6 is not a perfect integer power of 36. So if I said, well, what is the relationship between 6 and 36? One thing I could tell you is essentially that if we were to take the square root of 36, we would get 6. So what I'm going to do is I'm going to go ahead and spill the beans on this. I'm going to say the square root of 36, recall that if you were to write 36 to the 1/2 power, that is the same thing as if we were to write 36 to the first power second root, which is really just the square root of 36, which is plus or minus 6. Okay, so anyways, we could write 36 to the 1/2 power and really get this 6 that you see here on the right. And so the answer is 1/2, but how might I deduce this? And one thing I can tell you is, well, if both of these were 6 to the power of something, kind of like this here, if I were to rewrite this as 6 to the 1, and this is really 6 squared to the y, really I get this expression 6 to the 2y equals 6 to the 1. And so I just kind of wanted to go to show you that if 2y would have to be the same thing as 1, since 6 to the power of something equals 6 to the power of something, the two exponents would have to be equal, we get y as a half. So you just got to trust me on this one. Sometimes you'll see situations like, you'll get log base 49 of 7, and you say, well, that's a half too, because 49 to the 1/2 would be 7, because that's the square root of 49. You just got to be careful when you rewrite that there to kind of know that that happens. And then last but not least, radical notation. Now I want to make a note here. Often with radical notation of logs, we say if logs, let's put it this way, log expressions contain radicals. I'm just going to write this. Try rewriting, okay? Try rewriting having rational exponents, having rational exponents. And of course, the hidden math word in rational here is ratio. In other words, if I were to write something like this here, we say a, let's do this. Let's do, yeah, we'll do a. We say to the mth power nth root. I suppose we could say that we know that that's the same thing as the nth root of a, that to the mth power. But basically, we get a to the m over n recalling that our m here represents the power that we're taking our base to, and that the n here represents what we call the index of our radical here, what root we are taking. So the index or the root. And so when we rewrite this one here, we'd say log base 3 of, I guess, the 7th root of 3. I could say that this is the same thing as log base 3 of. Now rewriting this here, we say this is 3 to the first power, 7th root. So we get this log base 3 of 3 to the 1/7 power right here. And so if we were to rewrite this now, we say, well, what does that equal? Go around the bend. Let's go around the bend. We say, rewrite this. I bet you could find out a lot. We say 3 to the power of this y right here turned into 3 to the 1/7. And so what I could tell you is, because 3 to the power of y equals 3 to the power of this, the y and the 1/7, man, I'm telling you, those are probably the same thing, one-to-one property. So since those are the same, we could just kind of figure that out. So rewriting these things is a pretty powerful thing to do here. So let's look at a couple of really basic logarithmic properties. So we say, because logarithms are exponents, they have properties that can be verified using properties of exponents. We've seen properties of exponents before, like a to the, let's go a to the x times a to the y. Two things multiplied together with the same basis, you add the exponents, a to the x plus y. This is a property of exponents. So those kind of things apply here with logs, since a logarithm is an exponent. So let's start with this one. Log base b of b equals 1. Excuse me, because 1 is the exponent to which b must be raised to obtain b. In other words, yeah, what could you take b to the power of to get b? Looking at this, if you rewrite this here, you could clearly see that this says b to the power of 1 is itself. So this means that when you take expressions like log base 7 of 7, we're going to say clearly it's 1, because 7 to the 1 equals 7. Now also this, we say log base b of 1 is always 0, because 0 is the exponent to which b must be raised in order to obtain 1. So let's write this here. We would say going around the bend, and I guess we don't need to write it as we did up here, because that was written clearly right there, but also this one's written here. We're saying b to the power of 0 equals 1. And that's clearly always true for anything where b doesn't itself equal 0. So, of course, you wouldn't have a base of 0 in a logarithm anyways. But this is always true. When you take the log of 1, you get 0. So look at these two expressions here. Again, log base 9 of 9. Maybe you're having a hard day and you can't recall that 9 to the first power equals 9 and that we get 1 here. Well, let's just put it this way. If I can at least write it this way, let's rewrite this into exponential form. We'd say, okay, so here we go, around the bend. We say 9 to the power of y equals 9. And so we got 9 to the y equals 9 to the 1. I'm supposing that y probably equals 1 here. And then also this, we say, well, of course, the log base 8 of 1 is always 0. But again, if you're having a really bad day and all you get is this far, at least you can rewrite this into exponential notation and say, hey, 8 to the power of y turned into 1. So what the heck were you doing taking 8 to the power of something and getting 1? That thing must be 0. So these properties of logs are good to know. Log base b of b is 1 and log base b of 1 is always 0. But of course, you can always rewrite them and verify these things. So in this last little discussion we're going to have here, we've mentioned here that exponential things, of course, this would be an, let's label this here, this is an exponential function. And then the inverse of an exponential function would be a logarithmic function. Now this right here, logarithmic function, take a look at what I just wrote logarithmic function next to it. It still looks like exponential form, and it is, but when we rewrite it, excuse me, as a logarithm, look at what we get here. So we switched our domain and range, and so we get x equals b to the y. And so rewriting this here, we've got b to the power of y, of course, b to the power of y, equals x, turned into x. So this logarithmic thing here being the inverse of it, it's fair to say that we could call y equals log base b of x f inverse of x, since this is f of x. Of course, we write this f inverse of x with the little -1 here as a superscript. And we say that's equal to log base b of x. So since they're inverses, it just, something we need to be clear on is this. When you take the y values of one of these functions and plug it into the other function, it undoes it and sends it back to the original x value. Recall that when we take an x and a y and you plug it in under f, I'll just make this really brief here, f, we sent an x to a y. So what we're doing under f inverse is we're taking that y value and sending it back to the original x. So in other words, the output values for this function here are f of x values. If we take f of x values, take that y value, and plug it into f inverse of x. We're going to plug it into f inverse of x here. We get sent back to dun, 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 the original x value. And so this happens both ways around, but the bottom line here is this: because you can plug one into the other, let me scroll down here, then these two properties happen to be true. Of course we know, here, let me write this here. We say f of x, I just want to show you, f of x is equal to b to the x. You know, y equals b to the x is what we had for our exponential thing. And we say its inverse, I'm going to write f inverse of x is equal to log base b of x. These are inverses. So if we were to do this, let's say, you know, plug f of f inverse, we would get this expression here where we're plugging into f of x, which is b to the x power. So everywhere I see an x here, I'm going to plug in f inverse of x, and so I would get b to the f inverse of x. But what I know is that f inverse of x is this thing right here. So in other words, I get b to the power of log base b of x. So I'm going to come back to this here. If I were to do f inverse of f of x, which is the same thing here the other way around, then I would say, well, f inverse, this is log base b of x. I say log base b of, well, whatever x is here. And of course, I'm plugging this in here, f of x. But you guys, we know what f of x, log base b of x, f of x here is log base b of b to the x. So these two expressions here exist, of course, and this is what we're about to demonstrate in the table. But what we know is that in either instance, I guess I'll say that we should lead to this conclusion here that you just get x. And so what we're going to call these are our inverse properties of logarithms. And that is to say that when you plug one inverse into another, you just get x. But that's also to say that in this particular instance, that this is always true. So check this out. We say for any base that's positive and not 1, we say log base b of b to the x is just x. And what I want to point out here is this. Logarithmic things, which this is log base b, and exponential things. Look at this. Look, you're taking the log of an exponential thing. They undo each other. So basically, as long as your bases are the same, this like here and this here cancel out, and it's the weirdest thing, you just get left over with just the x. And the same thing is true the other way around. Look at this. We have b to the power of, look at this, but look what's in the power. A logarithmic thing. They're inverses of b to the power of something, but what's in the power? Oh, a logarithmic thing with a base of what? With b. The bases are the same. Then these cancel out with one another, and you get left with dun, 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 the argument on your logarithmic. So in general, we would say that logarithmic things and exponential things undo one another. Okay, so if all of this argument is confusing, check this out. Life never gets hard with logarithms because at least if you don't understand that by looking at this right here, we say log base b of b. Our bases are the same here, and this is an exponential thing. And so since the bases are the same, what I would tell you is that this and this kind of cancel out since we're taking the log of an exponential thing, and you just get 8. But I'll tell you what, again, if you're having a bad day, just write this here and watch what happens when we rewrite this. We would say 7 to the power of y equals 7 to the 8. Oh my goodness, if it's not clear that y equals 8, then I don't know what to tell you. So also this one here, looks like we have an exponential thing. Now, it's clear to me we have an exponential thing. Don't get confused by the log, but it's because we have 3 to the power of something. 3 to the power of all of this. And so I'm going to rewrite this into logarithmic form. But logarithmic form, recall, has log base b of something turned into something. What I have to do is I have to put in my little loop here so I can kind of make sense of this. So what's our base? Well, our base here is 3. And we took 3 to the power of what? Well, log base 3 of 17. And that gives us this question mark right here. So I'm saying, well, what did we get here? It's clear to me that if I took log base 3 of a question mark, and that's equal to log base 3 of 17, well, what the heck is the question mark? I would say the question mark and 17 are the same thing. So we get 17 having a bad day, and that's the right answer. So having a good day, what you recognize is, using our second property here, says if you have an exponential thing, right down here, exponential thing to a logarithmic thing and the bases are the same, they cancel out and you get left with the exponent. And what I notice here, or the argument here, is I had an exponential thing to the power of a log base 3. Those cancel out. You just get left with the 17 here. So cheers.